So now we're going to be talking about methane. In particular, we're going to be talking about methane hydrate in the Arctic. And indeed, the methane monster is roaring. There's a journalist named Dar Jamal, and if you're not familiar with him, please check him out on truthout.org. He's a very informed and steady journalist when it comes to the methane issue and also when it comes to all issues surrounding near-term human extinction. Please check out Dar on truthout.org. This is methane hydrate when it's first mined, and it looks pretty innocuous, doesn't it? It's white and, doesn't look like too much, but it's a really condensed substance, and indeed 1 cubic meter of methane hydrate actually equates to 164 cubic meters of methane gas. So it's got quite a conversion ratio when it thaws out, and that's a pretty stunning thing right there. As well, atmospheric methane is over 100 times more potent than CO2 as a greenhouse gas over a 10-year time horizon. That's because when methane hydrate first hits the atmosphere, it's at its full potency. And over 100 years, it degrades a lot, and over 10 years, it degrades some. But the thing to know about methane hydrate, it's much, much more powerful than carbon dioxide. Currently, though, only 13% of our annual methane emissions come from hydrate and permafrost in the Arctic areas. Most of our methane comes from other biologic sources, wetlands, ruminants, lakes, things like that. But right now, 13% is coming from the Arctic. However, as the methane begins to thaw, that number is expected to go up over time. So, methane is primarily a northern hemisphere phenomenon. It creates a global warming methane veil, which you can see here, and you can notice that it's primarily in the northern hemisphere, progressing along, I think, at about 1 kilometer a day or so. But it is more in the north than it is in the south by a long shot, as you can see. So the IPCC in their latest report did not really discuss methane as a dangerous substance, and they discussed it, but they didn't really discuss it in its potency, and they certainly didn't talk about the methane monster in its entirety. So what we're going to do here, we're going to look at it and do a deep dive right now. So in nature, methane occurs both in the permafrost and under the sea along the continental margins, and you can see how it occurs in nature, and it gets seeps and flares and all sorts of things like that. And here's an example of a methane flare, and it is currently coming out of the seabed in frozen form, and it's being held in place by a combination of temperature and pressure. But the temperature, as we know, is going up, and that's going to impact the methane emissions. In the ground, in the geology, it occurs in these gas hydrate zones, and it actually makes its way up through the surface through these disturbances in the actual geology, maybe when the land shifts or if there's an earthquake or something like that, but it creates weaknesses within the layers, it creates vertical weaknesses, and these turn into chimneys, and when the methane starts to thaw, it's seeking a way out because it's such a potent gas. It's so explosive, and it really it wants to come out because once it thaws, it's so much bigger. And so there are methane vents that have been formed around in the Arctic, and they've been named Pingo structures, and they can be fairly large, like 70 meters tall and 600 meters wide, which is pretty large, and that would be a pure chimney of methane coming out. So the global distribution of methane hydrate on the oceanic floor, it really occurs along the continental margins, and you can see just about along all the continental margins there are methane deposits. And one thing to understand about methane, it's just so much more plentiful than natural gas or oil or coal. Look at that ratio down here, the total volume of methane as compared to natural gas, oil, and coal. Methane is a very common substance. In fact, many countries are actually starting to mine it as an energy source, you can see on this map. So the thing is about methane, it hasn't really come out yet, and you can see here this graph updated for 2015. You know, the methane levels, they don't look really very dangerous. They're kind of flat. I mean, if you look at it, you know, since 1980, it doesn't seem like it's gone up that much. Well, everything is relative, and in fact, it has gone up a lot because it used to be, you know, 700 parts per billion. And when we extrapolate out to the year 2040, we see the methane starting to exponentiate and to come out a lot more strongly. So the methane levels, the last 800,000 years, prior to 1950, there were no issues with methane. It really wasn't a problem. Methane is measured in parts per billion. And prior to 1950, really the methane levels were around 700 parts per billion at its peak. And it, you know, had natural variations. As you can see, it went up and down, up and down, up and down with the carbon dioxide record. But prior to 1950, no problem. But what we find now is that methane is actually going exponential, and at some regions in the Siberian Arctic, it's actually releasing 100 times above normal. And that's a shocker, you know. If it was twice or 3 times, that would be significant, but 100 times is astronomical. So if we look at methane only as a gas and its, you know, levels over the past 800,000 years, we see that all of a sudden, since 1950, look at that, it's gone really straight up, and it's gone from around, you know, 800 parts per million to our current very high level in the 1850 area. The mean methane level was 1,846 parts per billion in August of 2015. Now, important to note, I know it doesn't sound very much, you know, parts per billion, that sounds like almost nothing. It's not really the parts per billion measurement that matters, it's the change and how much methane has changed over time. So you can see the change from 700 to, look at this, and now we're all the way up here. So you can see it's exponentiating at this point. And in fact, if you look at it just since 1985, what you can see is that there is a steady rise when it comes to about 2007 or so. It was somewhat of a plateau since like 98 to 2007. It was kind of flat, but it's taken off galloping at this point, and it hasn't come back, and we do not expect it to slow down. So the important thing to understand about methane, it's skyrocketing at this point past pre-industrial levels, and it fuels climate feedback loops, and this triggers even more methane. And of course, it's connected to all sorts of other climate feedback. So as the more methane comes out and the hotter it gets, the more other climate feedback loops get fired. In fact, if you look at methane just over the past 3 years, since 2013, 14, and 15, it's really easy to see that the methane levels are really starting to fill up. Now, these are selected altitude graphs, and the red towards the bottom of each year represents the air that's closest to the Earth, the atmosphere that's closest to the Earth, and the blue represents the atmosphere that's furthest away, like up more near the stratosphere. Methane likes to kind of hang out in the mid-levels, as you can see. And if you look at the graphic for 2015, look at this, you can see how much the methane levels have filled up. They're really much more saturated than they were in either 2013 and 14, which is stunning to know because it's been progressing steadily since 2007 without break. So this is a methane map, and the color to pay attention to here is pink. Gray is non-reading, white is, not part of the data. The satellite did not capture anything that's white. Those were misses. But what's important to understand is pink is very, very high. So if we look at this, we can see that methane is coming up here in Siberia really, really strongly. As well, it's coming up in the north of up the north of the Canadian archipelago and Greenland and other places as well. In fact, if you take a look most recently, July 19th through August 4th, just like 2 weeks or so, the methane is on a steady march up, and it actually is exponentiating, as you can see. And if you look at the next methane map from August 18th, look at the difference here. The pink is overriding, and anything that is pink is over 2,000 parts per billion. And that would be extreme methane measurements and emissions in those areas. Methane has two types of readings. When you talk about it, there's the daily peak and there's the daily global mean. So the daily global mean is like the average methane reading. And the peak is wherever that methane is being taken, what was the peak methane reading at that day? And you'll find there are a lot of peaks in methane readings. Methane is measured at Arctic stations throughout, and you can see here there are methane measurement areas in Alert, Canada, Svalbard, Norway, in Greenland, and a couple of places in Alaska. And it's important to have distributed methane readings because each place will log methane a little differently as it's the local area. So what we have been noticing with methane emissions over time, and this graphic going back to 1985 to the present with annual oscillations, you can see the up and down movement of the annual oscillations of methane. There are anomalous readings throughout, and every so often you get these WTF anomalous readings, and they're somewhat worrying because they could point to future methane levels and where methane will be. In fact, Jason Box, who works for the Geologic Survey of Denmark, has said if even a small fraction of the Arctic sea floor is released to the atmosphere, we're fucked. I don't think that Jason Box would say this casually, being that he is a doctor, he does study the ice, and that is his profession. So if he is saying something like this, then we can be sure that it's an urgent and pressing issue. So let's take a look at this measurement from Barrow, Alaska. There's a methane measurement station in Barrow, Alaska, and what they have seen in Barrow is that methane is actually rising by over 10 parts per billion a year. And you can see that the methane readings are showing up more and more strongly. If you take a look at this latter half of 2015 area right here, you can see that it's just more concentrated. There are more data points. So methane is coming up more strongly, and it's really evident. So at this point, we're going to talk about where does the methane hydrate exist and what affects it. So this is a picture of the Arctic if it had no ice. Greenland Greenland's center is lower than sea level, as you can see. But the important thing to know, and the reason I'm showing you this map, it's not the point that it has no ice. I wanted to show you the fault lines. And so there's a fault line that goes right up here through Iceland around Greenland and up here and through here. It's important to understand this because we're going to look at some patterns. And if you look at this area right in here, there's a lot of methane lodged right along here on the inside of this valley, and it extends up in kind of a T, and that methane is starting to come up. So here's how it actually looks. These are the methane deposits, and as you can see, here's that valley in the middle of the Arctic Ocean that we talked about, and then there's methane that kind of tees along on either side. But the area that is most problematic at this point is in the East Siberian Arctic shelf. And this is what we call the extreme methane emission zone. Methane is currently coming up pretty strongly, and you can see this in the heat anomaly map from last September of 2014. And if you remember our methane deposits map, the heat is actually mimicking the actual shape of the methane deposits. You might remember there were some methane deposits along above Alaska as well. So what we can surmise from taking a look at this temperature anomaly map is that methane is probably coming up here where the Arctic, and this is also where the sea ice is pulled away, and methane is coming up here very strongly. So this is the methane, extreme methane emission zone right in here. And here's another example of the Arctic Ocean. We can see the Arctic Ocean is red hot, which of course is anomalous. This is a temperature anomaly map. But it's interesting to see how hot it is compared to the anomalies on the rest of the oceans of Earth. And the Arctic Ocean is more anomalous than any other place on Earth, with possible exception of maybe, you know, the Gulf Stream or something that's really picking up heat as well. Now, there's another type of methane besides our biologic methane hydrate. It is a non-biologic methane, and it's called abiotic methane. It is created by chemical reactions in the oceanic crust beneath the sea floor, and it is something that's starting to come up right now in Svalbard. They have found many methane flares that are coming up right off the island of Svalbard, just to the west of it, and they're pretty big. And this is not from methane hydrate, but this is from abiotic methane. And what they've seen in Svalbard is that there are enormous 800-meter high gas flares that rise up from the seabed. Pretty startling. Natalia Shakova is an Arctic scientist. She also works with Igor Simoletov. Natalia Shakova was involved with the Sweras C3 mission to go through the Arctic Ocean and monitor the methane and get readings of all the different water methane levels around the extreme methane emission zone. She has said that she considers a release of 50 gigatons of methane hydrate possible. She doesn't say when, but we do know that it's defrosting and thawing out. So, you know, with that conversion rate, you can just imagine what that would do to the atmosphere if you know, that much methane actually hit the atmosphere. It would cause a raise in heat. She has seen high methane readings throughout the Laptev Sea. If you look here at the Lena River Delta coming out here, right there, these are areas that have high levels of methane dissolved in the seawater. And in fact, it was along these areas, this a close-up of the Lena River Delta. This is a record of her investigations with methane. And she and Igor Simoletov went along in the Sweras 3 mission and actually took these readings. And you can see the readings over here are much more heavy. That is expected because this is the discharge right here of the Lena River, and you would expect that the readings here would be much more heavy because that's where all that river water hits the Arctic Ocean. So subsea permafrost is melting in the Kara Sea, and the Kara Sea is a very shallow sea, and what they have seen is that massive seabed methane escape is happening in less than 20 meters of water. When methane escape happens in such shallow water, it means that the water column will not be able to absorb it before it hits the atmosphere. So in this case, there was a huge methane release in the Kara Sea, and you can see the resultant temperature rise is pretty stunning. Look at this It's 20 degrees centigrade hotter than normal, and this is very, very worrying that things can change this quickly. This shows that methane is a really dynamic gas and almost an instant heating agent. So as we see, massive amounts of methane escaped in water depth in less than 20 meters here in the Kara Sea. Now, what we see here is that the global methane levels, if you look at the year 2021, they're going to be going up to probably around 2,000 parts per billion, and that is going to cause additional heating.